Welcome back, geologists, and we're going to do the second half of unconformities, which deals with marine facies. Before we can even talk about marine facies, we need to discuss some basic symbols that are used in geology, things that can be translated through any language and recognizable. So here's a story I have on that. I was flying back from Hawaii one year. I was over there, and I was looking through some field course photos, trying to get organized for a magazine article that was going to come out. And I mean, we're talking like it's a night flight, and you don't want to have to talk to anybody sitting next to you. So there's a guy from China that was sitting next to me, and I'm sandwiched between him and another guy on the window. So you know how that looks, a three-seater, it's very tight. And I'm looking through my pictures of Zion National Park, and he goes, "Oh!" He gets all excited and starts waking everybody up. I mean, just because he got so animated, and I'm like, okay, what's up with this weird person, right? And he gets out some pen and paper and starts drawing rock symbols of what I was looking at. Right on the money. He started drawing cross bedding, he started drawing sandstone outcrops. He had been to Zion National Park. Turns out he was a petroleum geologist in China. Now, I didn't speak a lick of Chinese. He spoke very little English, but we both spoke geology symbols, right? So we could communicate very well. That's why it's important that you know lithologic symbols. Lithology refers to rock layers, and then the symbols are the symbols that are used in rock layers, on maps, on diagrams. Now, this is just a small version of what is out there. I mean, there is a rock symbol for every single rock type, specific characters of rock. So these are just basic stuff right here. So we're going to start, and we'll start with breccia and conglomerate. These two, take a look at breccia, notice that they have angular edges. And then look at the conglomerate, notice they're all different sizes and they're rounded. As you will learn, or did learn actually, as you learned in sedimentary rocks, rounded sediments represents a good distance travel away from the original place where that rock started or where it was made. If I have angular edges like we see in breccia, then it's going to be pretty close to where that rock was made or fell apart. The message is this. For either one of these, make sure that if it's breccia, you have angular edges, and conglomerates you have rounded, and that you have sediments of all different sizes. So to be clear, for testing purposes, you'll not only have to draw these things, but you'll have to be able to identify a drawing of them and name them by name. Okay, that's real important. All right, let's look at sandstone. Sandstone is drawn with all dots. So the Chinese guy that was sitting next to me on the plane started drawing rocks with little dots in it because Zion is made up of massive sandstone units. And then he started drawing crossbeds. That's when I knew for sure he was a geologist. And so they need to be equal size of sand grains, and typically rounded sand grains, because that's what most sand looks like. We'll come back to siltstone in just a second. Let's come down to shale. Shale is otherwise known as mudstone. Well, that's really fine-grained mud. So we draw that dash, 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 dash. It's so paper thin that it looks like paper layers. So in the field, I'll show you some pictures of this shortly, you can really see when shale is out there, it is so paper thin, it must take a lot of this mud material to make a layer at all. So that's really tiny grained stuff. Sandstone's much bigger. Okay, so and you learned in sedimentary that there's a size chart, right? So here is the big stuff, here's the small stuff. Well, when you get a mixture of the two, dash dot, dash dot, dash dot, that's siltstone. So make sure that you can draw each of these. Oftentimes I see people get confused with siltstone, shale, and sandstone, interchanging them because they don't understand the size comparison of each. We'll come back to coal in a minute. Let's do limestone and dolostone. If you look up in your field guides, the difference between limestone and dolostone, it's just one molecule of magnesium. That's it. So really, dolostone is a little harder, but there's essentially the same calcium carbonate stuff. So we draw limestone with bricks or all blocks. Those blocks are tilted to the side when it's dolostone. Now, volcanic rocks would be things that are extrusive igneous rocks. Literally, there are dozens of various different types of symbols for volcanic rocks. To make it easy, we're just going to use V for volcanic. And that's a pretty common denotation for some type of a volcanic rock. V for volcanic, right? Bunch of V's. All right, for plutonic rocks, which are intrusive, we're going to do that interlocking crystals you learned about in igneous lecture for test 1. Represents that interlocking matrix or phaneritic texture. So plutonic rocks are drawn like this, and most typically this is how granite is drawn. So there are a couple of other symbols for other intrusive igneous rocks like gabbro and diorite, but we're going to use this as the all-inclusive intrusive symbol for our course. Now, metamorphic rocks definitely have multiple symbols. This is a representation of foliated metamorphic rocks. Can you see how that compression is made for foliation and made the grains actually look kind of wavy? So that's how you draw metamorphic rocks. I haven't forgotten about coal. Now look at the lines and understand that coal is usually buried in muds. So that would be shale, right? Well, coal undergoes a form of metamorphism and gets squashed and heated up. And that's where the lines right through the middle, like little crosses, occur. So you're looking at metamorphosed mud that's enriched with biological material. You're going to need to know these symbols because they're basic symbols in geology that are used to interpret block diagrams, maps that are used for geology maps, and so forth. We're going to use it right away to interpret marine facies. So let's get started. Let's see how good your memory is. What symbol is showing right here? All blocks equals limestone. What symbol is all dots? If you answered sandstone, you are correct. What about all dashes? That'd be paper thin, so it's the tiniest one out there. That is shale. What is this one right here? Rounded clast conglomerates. What about next door? Tilted blocks to the side, one extra molecule of magnesium, that's going to be dolostone. What symbol is dash dot, dash dot, dash dot? So a little bit of sand, a little bit of mud, what would we call that? Siltstone. All right, what do the V's stand for? V for volcanic. Phaneritic interlocking matrix is drawn this way for all of our plutonic rocks like granite. So that brings me to the next step. Let's learn about sedimentary facies because you have to know how to draw the rocks to understand the block diagrams we're fixing to be discussing. A facies simply reflects just the type of characteristic of a rock. So I'm going to give you an example you might relate to. You look at a shot putter in track. Then I want you to look at the marathon runner. How do they look different? One's very built up, stocky, strong muscles, right? One's very lean from running long distance. Well, they're both athletes, right? But they trained a little differently, so their body plan looks a little different. Rocks do the same thing, except they're not training for track and field. Simply what happens is the type of environment that they're made in dictates the way that they look. So if they're in a high energy water environment, they're going to be a different size than they would be if they're in a really quiet, no currents, it's very dead water, it's just stuff to float down to the bottom. So that'd be really fine-grained stuff, so the character of the rock's going to look different. That's all a facies is. It represents the characteristic of a rock. In addition, that makes a distinctive rock type simply because of the environment in which it's made. So sedimentary facies are directly related to depositional environments that you learned about in test number 1. Each depositional environment has a special energy level which makes a signature pattern creating a specific rock type during deposition. For example, the shoreline and near shore is going to have pretty high energy. So the grains can be bigger simply because sand requires more energy. It's larger in size to deposit than something like mudstone or clay, aka shale. So you're going to find clay or shale in something that's a very low energy environment. Siltstone would be deposited somewhere in between. So it's going to have moderate On this side, probably moderate to high. On this side, moderate to low depositional environment energy. If I'm making carbonate mud, otherwise known as limestone, then it's going to almost be very, very low energy environments and a long way from any detrital stuff over here. Detrital meaning land derived, right? From materials of other rocks and fragments of stuff. So the higher the energy, the bigger the grain size can be carried in suspension either by wind or water. So that's why sand requires a higher energy level than something like limestone to be created. So looking at this, you can see why you needed to know some symbols. Limestone is the blue stuff you see here, and the color is totally irrelative. It's just to separate them visually for you to see. So I will tell you that limestone is formed in a marine environment, so the blue does have a little significance there. The green, see if you can see, it's shale, and it's drawn with all dashes. You learned that a minute ago. The dash dot is the silt, and the sand is done with all dots. So what's the significance of sandstone overlain by siltstone, overlain by shale, overlain by limestone? It's a natural progression of a transgressive facies. And you're like, oh gosh, that's a lot of words. You're fixing to learn it. It'll make sense. Now here's the deal. Limestone forms a long way away from the shoreline because it's very low in detrital material. To be exact, less than 50%, and in some cases, 100% of biological dead animals. Okay, so it's made up of microscopic animals. Sometimes it has macrofossils in it too. Unlike sandstone, which is almost exclusively detrital, so it's on the opposite end of the spectrum. With that in mind, sandstone forms at the shoreline and at the nearshore environment. This would be the beachy area of an ocean. So this is the shoreline where the water touches the continent or the island, and it's creating sands. The nearshore environment is going to be this stuff. You'll have lots of detrital material, but it's a little finer grain than the sand, so it doesn't require quite as much energy to be deposited as sandstone. But it requires more energy because it's a little larger in size than our shale. So where would you expect to find shale? Most shale in this progression of transgressions are referred to as lagoonal type of shales. It's a little deeper water, not quite as far away from the continent as limestone. And I hate to use the word deep because that's misleading. You can form shale in literally 50 feet of water in a lagoon. I've been diving and seen it made. So that's an irrelative term. You can have deep water shales, which are formed in the wide open oceans at the bottom of the abyssal plains. And they look different from lagoonal shales. But nevertheless, the stuff that's made pretty close to shore, that's called this type of shale right here. Limestone is formed far away from this important word right here called terrigenous. Let's get that word in your notes. Terrigenous refers to land derived. Land derived means you've got broken up, weathered, and eroded material that's washing off of a continent or an island. And then it's getting deposited into this water body, meaning the ocean. So the farther away you are from the shoreline, the less terrigenous material you should have that has not settled out of the water column. So limestone has a very small amount of detrital material, whereas sandstone should be almost exclusively detrital material. What that means is you're going to develop a specific rock signature pattern based on the energy that it's required to make that rock. So here is the shoreline right here. This is the area that's on the continent that could get flooded as sea level rises and falls, or high tide even comes in for that matter. And this is going to create an area like a swamp. Well, here's the actual shoreline. This is where I'd expect to go hang out at the beach. And on the beach, you can see there are very specific fossils that you can find during low and high tide. That's because they live in sandy environments for a reason. Notice that it grades laterally into the shale facies. This would be more of the lagoon, and specific animals live in a lagoon that cannot live right here. They just cannot handle the higher energy environments. They like more quiet environments where the water's not moving as fast. Way down here, I could have similar animals that might live here, but this is far away from the terrigenous input of the streams bringing in sediments from right here. So down here, I should have very little detrital material. Subsequently, I make 4 different rocks at exactly the same time. I'm making sands right here for the beach line, siltstones right in here at the nearshore environment. At the very same time, I'm making rocks in the lagoon, and at the very same instance, I'm also making rocks far away from the shoreline with very little terrigenous input called limestone. The point is that each one of these locations is making a rock at the very same time, and they're being deposited. So if I follow those rock layers in a lateral fashion, you could actually follow sandstone, then find siltstone, keep walking, you'd be walking a ways though, then you could find some shale being deposited, and ultimately, if you went far enough from the shoreline and found very little detrital material, you would be seeing limestone in the make. So that's important to understand, that we can lay down all 4 rocks at the same time. Well, as sea level changes over time, those 4 rocks are going to shift backwards and forwards sideways based on where the sea level is. That's what transgressions and regressions are all about. So there's this guy called Walther, and he came up with a principle or a law, and basically it says this: when a depositional environment in the ocean migrates laterally because of a sea level change, sediments of one depositional environment come to lie on top of another that were deposited in a prior sea level, creating a vertical profile of sea level change. In other words, a depositional environment changes. If that sounds really complicated, it's really not. So if you kind of look at this vertical block diagram right here, limestone's at the bottom, which would indicate an ocean environment far from a terrigenous input of sediment. You just learned how limestone formed, right? And then we know shale is the lagoon, right? We know dash dot is going to be the siltstone, which is going to represent the near shore, and sandstone is the beach. Well, the law of superposition says limestone's the oldest because it's at the bottom, right? And sandstone's the youngest because it's at the top. So what that means to me is there was a beach most recently at that top layer. And this would have been a natural progression of sea level lowering, with beach being the most recent depositional environment in exactly the same place that used to be wide open ocean and the perfect place to form no terrigenous input or limited terrigenous input limestone. So let's kind of look at it over here. That's the same area that you're seeing right in this section right here. So we're getting very little limestone forming because the sea level's lowering, and you can't make limestone if it's too close to the shoreline. It just doesn't work. So this can happen both in a transgression and a regression. In the case that you're seeing here, we're getting a regression. So the sandstone at the top would be this rock right here, and that's representative of a shoreline environment. All right, so you put them side by side. You can see they're inverted block diagrams. Again, this is the one you just saw with the sandstone at the top representing a beach with the most recent environment. This is exactly the opposite. Limestone's on top, so what does that mean? It means that the most recent environment, rock layer, was far away from a terrigenous input. So it was making limestone. That means I had a transgression. So this is your transgression diagram. This is your regression. If you go backwards, you can see the next youngest is your shale. That would have been as sea level was rising from the beach way down here. This became the next depositional environment, directly deposited in X marks exactly the same location, so the same GPS coordinates. Then it got a little deeper or a little further from the continent and was in good conditions to make lagoons, and then eventually the water was rising enough that we created the right depositional environment for limestone. So when I see this pattern in the field, that tells me I had a rise in sea level. When I see this vertical arrangement with limestone at the bottom and sandstone at the top, that tells me we had a perfect regressive sequence in place. So you may be thinking, could you have an absence of one of these rocks? Absolutely, depending on where you are and where the rocks are found. And I'll demonstrate that in just a minute. So what are the causes of these sea level changes? Let's start with transgressions. First sea level change cause of a transgression would be the melting of polar ice caps. You're like, well, duh. Really, you need to think more about that. It's not just the land, and really, it really is not very much as related to land glaciers as much as it is to sea ice. But when we get a major ice age that melts, global sea level rises. That's the concern, a part of the story of climate change, especially when we're looking at the Arctic Circle today. Lots of our population lives around several miles of the shoreline all over the world. And so to rise sea level, even by a few feet, could mean displacement of people all over the world. Number two, when we have a really active mid-oceanic ridge, in other words, we get mountains at the bottom of the ocean, that's going to displace water and spill it onto the continent. So I have a childhood story to tell. You probably had brothers and sisters when you were like 1 that y'all all took a bath together. You may not remember it, but your parents probably do. And I can remember I was about 2, and my brother and I had to take a bath together. We were just little bitty kids, so it was okay. And my mom had put him in first, and I was going to go in second. And she just put a little bit too much water in that tub. So what happened when she put me in there? You can almost see it. You can hear it, right? The water spilled out of the tub, went everywhere, made her so mad, right? Well, I'd like you to imagine, instead of being people, let's make mountains that are growing at the bottom of the ocean, and it's spilling that water onto the continent. That is definitely indicative of when you have very active mid-oceanic ridges that are growing taller mountains at the bottom of the ocean. The third way that I can get a transgression is if I get localized subsidence on the coastline. So let's say, we'll take New Orleans as an example. New Orleans, not only is it below sea level, built below sea level, that's strike one. Number two is that the land's being subsided because of groundwater consumption causing the land to sink. So as the land sinks, obviously it's going to get flooded, right? So those can be examples or causes of transgressions. Let's talk about regressions. Regressions can happen because an ice age forms and you begin to suck up a bunch of ocean water because of sea ice. Second way, I don't have hardly any activity at the bottom of the ocean where mid-oceanic ridges are, so my mountains are very small, if any, and that means there's less volume displacement at the bottom of the ocean, so the water sinks off the continents and rests in the ocean basins. So in other words, we didn't have any people in the tub, right? Number three, we get some kind of uplift in the form of mountains at a shoreline. You can see how that would change sea level in a localized area, right? But when we're talking about transgressions and regressions, we're usually referring to eustatic sea level changes, which refers to global sea level changes. To be exact, there's been 6 of them. So let's define regressions and transgressions and show you examples of both. The prefix, means to retreat. So when you get a regression, you're looking at sea level dropping. So the sea level floor is exposed in areas that used to be submerged. I should see an increase in the volume of sandstone production. So now that you know this is all dots, this was my original sea level. Sea level got lowered to here next, and then to here. So see how my volume of sand's growing? I used to be able to form limestone here, and now at the most recent sea level on top, I can only form sandstone. Why? Because the shoreline moved back towards the ocean. And when that did that, I lowered sea level. I could no longer form limestone because remember, limestone requires to be formed far away from a terrigenous input. So this is the most new place I can form limestone. Well, I was cranking that out like a lot back in my first sea level. But I can make sandstone because I'm near the shoreline. And that grades into siltstone, into shale, and then into limestone. So if I keep lowering sea level, we wouldn't even be making limestone in this area. But if I rise sea level, I should see an increase in limestone. So I'll tell you a trick for your test. The way I kind of determine these charts that grade laterally like this, if they're a transgression or a regression, is to look at the volume of limestone. If the volume is shrinking, and in this case it is each sea level, I went from a whole bunch down here to less here and a lot less right here, sea level must be lowering. On the flip side, if I see an increase, this would be inverted, where you have more limestone up here, less here, and very little down here, that would be a sea level rise, which is called a transgression. So regressions can make a progression of sea level. So this used to be your beach with sea level 1, this is sea level 2, and this is the most recent sea level, which is sea level 3. So that's what SL refers to, SL3, SL2, SL1. So a regressive sequence will have coarser grained rocks like sands that continue to get laid on top of finer grained rocks such as limestones and shales. So I should see more increase in sandstone and less of my finer grained rocks that require a low energy environment like limestones and shales when I'm in a regressive sequence. So going to transgression, the term trans or prefix refers to invasion. So if you get a transgression, the sea is invading the continent. So this happens in places like Texas have been covered for an extensive period of time by a transgressive ocean, at least 6 times in geologic past, right? So the most recent one that you're familiar with that swept down all this limestone in the Waco, Texas area happened back in dinosaur time frame. So this floods out areas that used to be exposed, land that you could walk on, and covers it with an ocean. It's almost imperceivable what that would look like, isn't it? But it does happen, and it's happened, and we've got a rock record to prove it. So a rise in sea level that covers a previously exposed land is called a transgression. So here's sea level 1. We're a good distance away from the shoreline. This is the only place I can make limestone. I rise sea level, the beach has moved from here to here, and my second sea level. Notice how my limestone grew. I moved my beach all the way to here, because remember this was my second sea level. Here was my initial sea level coming back to here. You can see my sands, my beach are moving up onto the continent, and as I do, I can make limestone in places that I didn't used to. So let me give you an example. Let's say the current shoreline's in Galveston, Texas, and I rise sea level and put it in Houston, Texas. So let's just say we went from Galveston to Houston, right? So I covered all of Galveston, and now the beach is in Houston, Texas. So I'm not going to be able to walk around in Galveston like I used to. So let's say a third sea level rise, I moved the shoreline from Houston to Aggie Land. That'd be interesting, wouldn't it, to put a beach in Aggie Land. So College Station now has the beach line. Houston, Texas, with its 4 million plus people, are now underwater. You got to be a fish to live there, right? Or a coral. So I'm going to be making a different rock back in Galveston, wouldn't I? Because I'm in a new depositional environment. I'd probably be making some limestone if I were in Galveston, but I'd probably be making silts or shales if I was in Houston. But I'd be making sandstones if I was in College Station because the beach is there, right? So let's say I rise sea level again to Waco, Texas. We're now the beach. We'd be making the sands. College Station would probably be making the siltstones or the shales, and I guarantee you Houston and Galveston are far enough away from our shoreline that they'd probably be making limestone. So I rise sea level again, and I put it all the way in Lubbock. So what would Waco be making? We're a long way from Lubbock, aren't we? We'd probably be making limestone, and so would everybody else behind us, because we're just not in the right place to be making shales anymore or siltstones. So sea levels usually are not that dramatic that fast. They rise and they fall, and you can have slight sea level changes that actually make rock segments change even within the same geologic period, from limestone to shale, or from shale to siltstone, or from siltstone to sandstone. Or you can basculate back and forth between limestone, which would be far away from a terrigenous input, up to shale, which is lagoon. Then you rise sea level again, and you'd end up with the limestone. You lower it a little bit, you end up with the shale. So you get stacked, one on top of the other, a vertical rock record of sea level change. So a transgression should have finer grain rocks that were made in lower energy environments, like the places I would have lagoons or far away from a terrigenous input limestone being made. I should find a higher concentration of coarser rocks like sandstones and siltstones because we're not going to be in the right depositional environment. I should have less and less of that material as the beach marches itself onto the continent. So notice what I told you earlier about limestone growing from sea level 1 to 2 to 3. See how it's bigger here? The reason it is, and it's moved closer to what used to be the initial shoreline, is because I've moved the entire shoreline onto the continent in a different location. So I can make limestone in more places that I didn't used to make it. So here's my sea level 1 and then my sea level 2. Notice the beach went from here to here. Do you see how my limestone moved from where it used to be only made here, and now it's moving all the way up to here because the environment's a better place to put it. I moved it up a third time, and can you see how my limestone grew in a place where it didn't used to be, simply because I moved the beach further onto the continent. So these diagrams will be on your test and quizzes, and you'll have to identify, are you looking at a transgression or a regression? In review, look in the concentration of limestone. In this picture, you can see the volume of limestone from sea level 1 to 3 has increased, which tells me the sea level has moved onto the continent, invaded the continent. That would be a transgression. This opposite would be true with the regression. As the beach marches back towards the ocean, I should see less and less limestone. So there's more limestone here, less here. That tells me the sea level dropped. Do it a third time and you can see I can barely make limestone on this third section. That's because the beach is moving back out towards the ocean. So I should see coarser rocks overlying finer grain rocks because the depositional environment's changed. The end result is this. You'll get multiple transgressions and regressions simply with a small change in sea level, which ends up giving us a zigzag pattern appearance. So let's focus in on this section right here. It's really easy to see. So I have a small a medium transgression, a small regression, a big transgression, a small regression, a big transgression, a small regression, a very large transgression, a big drop in sea level or regression. Small transgression right here, big regression. Small transgression, big regression. Tiny transgression, pretty big regression. Tiny transgression, medium regression. Do you see how that pattern's working? What's happening is every time I'm moving the sea level towards the continent, I get a stretch or an arm that comes out this way where limestone can be made in more places. Where I have a regression, limestone can't be made there anymore, and instead shale is. So in the Waco area, this is the profile you'll see in most of our rocks. If you move to where the shoreline was at the same time that these rocks were being made in Waco, you would see this profile. So if you go out towards West Texas and even further towards the interior of the continent, near Utah, you can find a lot of this stuff from the same time period. So you have to understand that this is regional rocks. Would there have been sand in our area? Probably for a brief period of time, but it's probably eroded. Remember unconformities? So we may have an unconformity there. Somewhere there's a beach rock that matches our limestone and shale that we have a lot of right here in central Texas. So this is an area called Lover's Leap. And in part of this area now, this is smooth rock because we've had some mass wasting, some rock slides. Don't be deceived that this in, out, in, out, in, out is what you're seeing here. While it may be the same story, this is caused by differential weathering. So the limestone's harder than the thin rocks in between. I'll zoom in on the thin rocks. These are going to be the paper thin layers drawn as all dashes. You know that as this rock right here, shale. The big blocky stuff right here are these things right here. So you can almost see why a geologist would draw limestone with all blocks and why a geologist would draw shale with paper thin layers, right? You can envision that. So I'm going to ask you, which one's the transgression in this? Is it the left diagram or is it the right diagram? And then I'd ask you why. So you kind of have to piece it apart. Where was the marine environment most recently? So you should see limestone there. So limestones with all blocks, that would trump and make the left diagram the actual most recent transgressive sequence. This would be a regression at the top. So on your test and quizzes, not only will you have the lateral diagrams, you'll also have these that you have to identify as a transgression or a regression. So here are the lateral diagrams. Where's the transgression in this picture? Remember, you'd be looking for increasing volumes of limestone from sea level 1 to sea level 3. So if you said the bottom diagram, you are correct. If you said the top diagram, you're actually looking at a regression because the beach went from here towards the ocean and again back towards the ocean. Look at the concentration of limestone. It decreases with each sea level. So if I had a transgression, the limestone should increase with the most recent sea level change. So here's that Lover's Leap again, and these ledges, now it's pretty nice and smooth because we had some rock slides, but this really shows you the inside sections here are because of differential weathering. So the nice smooth layers that are out there right now actually show you really well the alternating layers of mud known as shale and the transgressive ledges. But nevertheless, this shows the blockiness of that. So these Alternating layers, if you start counting, Lover's Leap has between 20 and 30 sea level changes over the course of probably about 50 to 60 million years of time. That's remarkable because we have a documentation that sea level gradually went up, came down, gradually went up, came down. So we were in the limestone and the shale sequences over and over and over, at least 20 to 30 times during the Cretaceous. This really shows up close what you're looking at. So the big blocky hard stuff would be the limestone. So that's going to be full transgression, and this is going to be a slight regressive sequence where you see the paper-thin rocks where the shale is. So this is actually a form of shale called marl, M-A-R-L, which is kind of a carbonate mud. And so I see multiple sequences of this stuff going up and down. What does that tell me? That we've had multiple sea level changes in geologic past in this area. This really shows it well. Can you see the paper-thin layers? We would draw that with all dashes. The thick, blocky stuff we would do with blocks. Those are limestone. So what's the difference? This would be a lagoon environment. This would be far away from a terrigenous input. Just a slight sea level change. What you need to really grasp and put your arms around is these sea level changes happened in exactly the same GPS coordinate location. So that means during the Cretaceous period, when all this limestone was being made, sea level was constantly at a state of change, taking us from a lagoon setting to a far away from a terrigenous input setting back to a lagoon. Limestone setting, shale setting, limestone, shale, limestone, shale. It's almost repetitive, right? So we have this evidence. If you go other places in the world, it might be sandstone and siltstone that you're looking at. Sometimes you can see all of the rocks. There's a place in the Grand Canyon you can see a perfect transgressive sequence from going from sandstone all the way to limestone. And it's where the first major sea level I was talking about out of the 6 occurred in the North American craton. So you see an ocean here covering land. Would that be a transgression or would that be a regression? If you answer transgression, you are correct. So this is actually the Great Barrier Reef. This area during a regression would be exposed. We're more in a transgressive sequence right now where this area is covered. But let's say this was Waco, Texas, and we were covered with this kind of water. This would be a transgression. Hard to imagine that this is what we looked like back when the rocks around here were being made. But that's nevertheless, that's the case. So you might go, oh, well, that is obviously a regression. Well, we got an ice age going on, so water is not available to flood the continent as much. Sea level drops, the land's exposed, so that would be a regression. So you're going to have changes in sea level based on climate changes, mid-oceanic ridge development or a lack thereof, and certainly localized subsidence or localized uplift. Remember, those are the 3 reasons that cause a transgression or a regression. Do you remember what this was from our last lecture? So this was evidence of an unconformity. See if you can name which type. Is it a disconformity, an angular unconformity, or a nonconformity? So you can see the angled, tilted beds of sedimentary rocks overlain by some kind of a definite type of breccia right here, and the unconformable contact. So this is an angular unconformity. Let me tell you that if this was sandstone, and right above it, I had siltstone, shale, and limestone, and be looking at a perfect transgressive sequence. If it was flip-flopped and sandstone was at the top, I would be looking at a regressive facies. I would tell you that we had probably desert sands right here, and I've been there to tell you that's what they were. So this is not representative of a transgressive or a regressive sequence. But if this was limestone directly above it, I would definitely say that that would be a transgressive sequence. Nevertheless, let's conclude. Remember, this is an unconformity, and an unconformity represents a gap of geologic time. I'll see you at the next lecture. Bye.